Okay, so welcome back, everybody. Thank you very much for coming back to the other Zoom channel. Okay, so it's a great pleasure to introduce Brendan Hassett, who will continue also his nice talk series with his second talk today. So let's get started. So it's a pleasure to introduce Brendan Hassett, who will speak on loci of rational varieties. Thank you.
Thank you, Carlos. So my two lectures are actually not that tightly related to each other. So if you didn't attend the lecture yesterday, I think you will not suffer at all. I'm going to talk about something that has some connections, but is largely independent logically from what was discussed yesterday, although the circle of ideas are related. So thank you to the organizers for giving me the chance to present. This reflects a suggestion from Ludmil that I try to give a survey type talk. And so this survey is on loci of rational varieties. And I really have two parts to this. One is to give a high level overview of what one knows from a structural perspective and what one would like to find. And then I'm going to do a deep dive on cubic fourfolds, one of my longstanding favorite topics, and just to show you how what we know about these varieties, how it dovetails with what we hope to establish on a more general basis. So there's really two parts to the talk. So let me start with the first part. So let me, hopefully I can get the, okay. So this is the general context. So I want to mention specialization results because these really give the most precise and general information about the structure of loci of rational varieties. So I'm always going to consider pi from X to B a smooth projective morphism. I will always focus on smooth projective varieties, and I'm not going to allow singularities except with one small exception. And so we're going to let X sub B be the fiber over a point B of the base. The base will always be irreducible, or at least connected over the complex numbers. We're really interested in properties that are constant and connected families. So let's take B. We could take B to be smooth and irreducible without any harm. And so the two statements that have been established in the last few years, the first is due to Nicaise and Schinder, a beautiful theorem that asserts that if an element of the family is stably rational, if a general element of the family is stably rational, then all of its specializations, its smooth specializations, because of my assumption on pi, remain stably rational. So in smooth families, stably rational varieties specialize to stably rational varieties. And the second statement, which came shortly after the first, is that the same holds true for rationality. This is true to Kontsevich and Schinkel, namely that if you have that a general fiber of the family is rational, then every fiber is rational. And so this means that stably rational varieties specialize to stably rational varieties specialize to rational varieties. And so this has important implications for the loci of rational varieties. So maybe I'll say more specifically what I mean by that next. So the loci I'm going to consider is rat B. So these are the points in the base of the family where the corresponding fiber is rational. And stab rat B, these are the points of the fiber of the base where the fiber is stably rational. Obviously, rational varieties are stably rational. The other implication is generally false. There's a beautiful theorem, Bovio, Colliot-Tillens, and Sukin-Swinnerton-Dyer showing the existence of smooth complex projective varieties that are stably rational but not rational. That won't play a huge role in what we're doing here, but I just wanted to mention it. And so the structural results of Nicaise, Schinder, Kontsevich, and Schinkel is equivalent to the assertion that rat B and stab rat B are a countably infinite union of Zariski closed subvarieties of the parameter base B. So each of these Zariski closed subvarieties is closed under specialization, but there could be a lot of them. There's no reason to think that there's only a finite number of these. And in fact, there are counterexamples that we'll discuss in a moment. And so we have some qualitative structural information about what the loci are of rational and stably rational varieties. They're built up by putting together a countably infinite collection of subvarieties of the parameter space. And so one of the guiding questions I'd like to explore is, so we have these implications, the empty set, the locus of rational varieties, the locus of stably rational varieties, and all of B. And so basically the way to think about this is, so to what extent can these various inequalities be strict? Another formulation of part of this question is whether, or to what extent, rationality and stable rationality, are they deformation invariant? That is, if the rationality locus is non-empty, is it all of B? If the stable rational locus is non-empty, is it all of B? Obviously, there are many numerical and topological invariants that distinguish general varieties from rational and stably rational varieties. A stably rational variety has trivial fundamental group. You have non-vanishing. So if it's stably rational, holomorphic tensors will vanish. You don't have torsion in certain degrees. There's a lot of topological properties that are in fact deformation invariant. They can be used to distinguish rational varieties from more general varieties. And so for most of the first, I don't know how many millennia this has been studied, those were really determinative in describing how these different loci interact with each other. However, recently, maybe 4 years ago, we found that rationality is not, in fact, a deformation invariant. And so for fourfolds and higher dimensional varieties, there are cases where the rational locus is non-empty, but is strictly contained in the base of the parameter space. And I'm going to show you an example. This is due to myself, Alina Prutka and Yuri Chinkel. And so look at all the hypersurfaces in a product of projective spaces, P2 cross P3, that have degree 2 in each set of variables. So you can think of these as being fibered and conics with respect to the second factor, and fibered and quadric hypersurfaces with respect to the first projection. And so the assertion is that there are, in fact, a countably infinite collection of codimension 3 subvarieties in the base of this family that parameterize rational examples. One can show, using techniques of Poisson, that these are in fact dense in B for the standard complex analytic topology. However, a very general such hypersurface is not stably rational. And in particular, if it's not stably rational, it's also not rational. And so this gives you some information about what kinds of inclusions can happen. So some strict inclusions are possible, even when the rational locus is not empty. And so I'm going to give you a Cliff Notes version of what the argument is. And so basically, one part of this is relatively straightforward. If you look at the projection onto the P2 factor, these fourfolds are fibered over P2 in quadric hypersurfaces. And the standard stereographic projection argument tells you that if you have a quadric hypersurface and there is a rational point or a section, by a section here, I mean a rational section, doesn't need to be defined over all of P2. Such a rational section suffices to guarantee that the fourfold is rational because it's rational over the function field of P2. On the other hand, these powerful techniques by Poisson, the decomposition of the diagonal, can be used to show that a very general representative of this moduli space is not stably rational by degenerating to a carefully chosen configuration where there is actually unramified cohomology in the desingularized sort of degenerate version of this family. And finding that explicit example is largely the key to making this argument work. So In dimensions 4 and higher, we have cases where rationality is non-empty, but not all members are stably rational. Are there any questions or comments?
Can I ask, do you know anything about whether those which are not rational are birational to each other, or nothing like this is known?
I don't think I know the answer to that. I would suspect that there can be non-trivial birational equivalences between the elements without them actually being birationally trivial, but I have not thought about examples. I will come back to this. I know examples like this for cubic hypersurfaces, and I wouldn't be surprised if there are examples in this context, but I don't have a specific one in mind. There are, of course, yeah, so, but I would, if I were a betting man, I would put money that there are cases where they're non-trivial representatives. I think there are some results about birational equivalence among the, among hypersurfaces that shed light on this. I think, is it Schreier? I could be wrong, but I think there are papers, but I'm not sure whether it gives, to what extent it applies in this situation. So stable rationality is also not a deformation invariant. And so for varieties of dimension at least 3, there are examples where the stable rationale locus is strictly contained in the base, but is non-empty. And so these examples come from threefolds that are fibered in conics. They're fibered in conics over a degree 5 Delpetzel surface or a mild degeneration of a degree 5 Delpetzel surface. In each case, the base of these conic fibrations are a surface blown up at 4 points. The degeneracy locus of these conic fibrations is a bi-anticanonical divisor in the surface. This is a result that we obtained with I obtained with Andrew Kresh and Yuri Chinkel. And so here I can't really, I could give a whole talk summarizing the argument, but I wanted to sort of just give examples illustrating the possible inclusions that could appear. So I won't dwell on this too much. In the specific example that we look at, the locus of rational examples is trivial. So we don't have strict inclusion in the first containment. So for threefold, stable rationality is not deformation invariant. And so from this perspective, I just wanted to put my finger on some of the natural questions that I think are worth asking. Maybe some of you know answers to these questions. So please pipe in if you have ideas as to solutions to these. But these are questions that I'm interested in. So throughout, X over B is a family of smooth projective varieties over an irreducible complex base. And so one question is, it would be fun to find examples where all the inclusions are strict. I don't know a concrete example like that, and I think it would be interesting to exhibit such an example. Is there a case where the rational locus is non-empty, but strictly contained in B, where you can actually compute it? I am not aware of an example of families where you have a complete characterization of the rational locus, except in cases where it's empty or the entire base of the family. So this is kind of a frustrating point. We have beautiful tools for showing that very general varieties are not stably rational, but it'd be nice if we can say with a bit more precision exactly which ones are stably rational and which ones are not. Another chestnut that's been around for a long time and it always seems like the three-dimensional case is the last case to be fully resolved in any geometric problem. So is rationality deformation invariant of smooth threefolds? So as far as I know, this is still an open problem. Whether a smooth threefold, whether its rationality is preserved under small deformations. And finally, is it possible to find non-rational hypersurfaces that are stably rational, especially for cubic hypersurfaces? So all of the known rational hypersurfaces are cubic. I don't know if there are higher degree hypersurfaces that are stably rational. I think it's an open problem to exhibit quartic hypersurfaces that are rational or stably rational. And so it would be interesting to shed light on whether there are cases where the strict inclusion between rational and stably rational, whether I can see those on hypersurfaces. So I'm sure probably some of you will know solutions to these questions, so I'll pause a moment. Okay, we'll come back to these maybe at the end of the talk, but I just wanted to sort of lay out some general questions about the loci of rational varieties that, as far as I know, are still open to study. All right, so what I'm going to do now is I'm going to turn to a sort of a case study where we can hope to try to say a bit more about the structure of the locus of rational varieties. And so this case study is probably the most extensively studied situation where there is an expectation that some will be rational and some won't be rational. And so let me introduce these. I know there are many people in the audience who know these examples very, very well. And so I apologize if I dwell a little bit on the classical picture, but I want to sort of show where the first constructions come from and then put them in a more general context. So the simplest parameterization is if you have a cubic fourfold that contains two disjoint planes. In general, an even dimensional cubic that contains linear subspaces that are disjoint of half the dimension. This argument will work. And so the basic idea is that you take a point in the first plane and you take a point in the second plane and you draw a line joining those 2 points together. And if the points P1 and P2 in the planes are chosen sufficiently generally, then you get a line that meets the ambient cubic in precisely 3 points. And you simply take the third point of intersection of the corresponding line with the cubic. So this third point construction gives examples of rational cubics in all even dimensions. And so I wanted to write down a little bit more detail than I probably should here about exactly what shape this takes in terms of equations. And so I basically just take the linear forms defining P1 and P2, and I organize the defining equation of X in terms of those variables. And the defining equation can be written as forms of bidegree 1, 2, and 2, 1 in the corresponding 2 triples of variables. And so the reason why I'm doing this is that the indeterminacy of the map from P2 cross, or from P1 cross P2 into X, it just coincides with those lines that are in fact contained in X and incident to the 2 planes. And this is a K3 surface. So it's a complete intersection of forms of bidegree 1, 2, and 2, 1 in a product of P2s. And so you get a beautiful rank 2 K3 surface that parameterizes the indeterminacy or the locus that's blown up by this parameterization. So the next example goes back to Maureen Fano and Beauville-Donaghy. I think Fano understood it much more clearly than Maureen did. I think Maureen originally hoped to use this as a proof that all cubic fourfolds are rational, but the parameter counts don't quite go your way. And so it only gives you a special locus. In any event, you look at a quartic scroll, which is just a copy of P1 cross P1 embedded in P5. And it's embedded via forms of by degree 1, 2. So you get a quartic surface in the projective 5 space. And so note that the linear system of quadrics cutting out P4, it collapses all the secant lines. And so, so you get a map from the P5 that contains the a ruled surface to a quadric hypersurface, also in P5. And any cubic fourfold that happens to contain our scroll is mapped birationally onto Q, this quadric hypersurface, by the secant construction, and therefore is rational. And so this gives you another collection of rational examples. So the parametrizing map, the reverse map from Q back to the cubic fourfold, Q is the quadric hypersurface. And so it's obtained as follows. If you take a degree 14 K3 surface embedded in P8, so this is a linear section of the Grassmannian of two-dimensional subspaces in a six-dimensional vector space. So you have a fairly explicit equations for these K3 surfaces. And you take a double projection from a point. If you count parameters, it will generally be contained in a quadric hypersurface. And there's an explicit linear series of cubics containing this projected surface. And that explicit linear series will map the quadric onto the cubic fourfold. And so, again, remarkably, we have a K3 surface that arises naturally from these birationality constructions. So here is my only exception to the rule that I will restrict attention to smooth examples, but the visibility of the K3 surface makes this one hard for me to exist. So suppose that we have a cubic fourfold with a double point. So this is an ordinary double point isolated x0. Any cubic hypersurface with a double point, if you project from the double point, you get a birational map from the cubic into to projective space. And so here you get when you project from x0, you get a birational map onto P4. The inverse map can be written down completely explicitly just by expanding out the Taylor expansion for the defining equation of x about the point x0. And so I've done that. There's a quadratic term and a cubic term. And where the quadratic and the cubic term simultaneously vanish, it gives you the lines contained in capital X and containing x0. And so here you have a degree 6 K3 surface. So K3 surfaces arise quite a lot in these classical constructions. So I'd like to step away and to try to sort of look back at the general classification structures with the benefit of hindsight. So most of these structures, they were found long before the sort of big picture theorems, Nikai, Schinder, and Kontsevich-Schinkel were discovered. But I think that with the benefit of hindsight, we can kind of see these classifications as being inspired by an expectation that these structural results should hold true. So let's return to these with this benefit of having some additional theorems under our belt. Actually, are there any questions before I go into this? Okay, I'll continue. So let's consider the moduli space of all cubic fourfolds. So smooth cubic fourfolds in P5. It is 20-dimensional. And so I'm going to think of this as a base of a family, abusing notation a little bit. I guess it might be more correct to look at the projective space, the P55 parameterizing all cubics, and remove the discriminant locus. But just for simplicity, I'm going to focus on the moduli space rather than an actual parameter space of hypersurfaces. So the Hodge numbers of this are known, and they're given as follows. And we have, due to Voisin, the period map for these cubic hypersurfaces is in fact an open immersion into the period domain, a type 4 Hermitian symmetric domain. So this is very analogous to K3 surfaces. Nowadays, there's work of Laza and Luyanga that completely characterize the structure of this map and what the complement are. And so these period maps are extremely well understood from the perspective of modern technology. When you have a general cubic fourfold and you look at the Hodge classes in the middle dimension, so the Hodge classes in H4, a general cubic fourfold away from a countable number of special subvarieties, it has just the square of the hyperplane class. So those are the only algebraic cycles in the middle dimension. But it's possible for a cubic to have additional cycles beyond the hyperplane class. And in that case, we'll say that the cubic fourfold is special. And so when I was a student, I never heard Barry Mazur or Joe Harris say this in quite so many words, but this was definitely the impression I got. So that's the question marks. And so the speciality conjecture is simply the assertion that all rational cubic fourfolds, so the locus rat C, are in fact special. And the special cubic fourfolds can be described quite explicitly. They're indexed by a countably infinite union of irreducible divisors and moduli. They're parameterized by even integers congruent to 0, 2 mod 6, starting from 8. And the first two cases are cases that we've already seen. So if you have special cubic fourfolds indexed by C8, these are just those that contain a single plane. And the ones of discriminant 14 are those that contain a quartic scroll. And these were the rational examples I showed. C8 can cross itself. It's possible for a cubic fourfold to contain more than one plane. And the self-crossings where the two planes are disjoint is also rational. And so there are instances of rational examples in C8 as well. So let me just say for the moment that as far as I know, I mean, I've seen some talks about this, but I haven't seen written theorems. I don't know a proof that gives that any cubic fourfolds, any smooth cubic fourfolds are irrational. So hopefully someone will contradict me on this. Maybe I should pause and let someone contradict me. I've seen very interesting ideas that might yield this, but I think we're still, yeah, this is something that we're still collectively working on. So I've spent a lot of time looking for rationality constructions in various cases. And so some of the cases, for example, if you have a cubic fourfold containing a cubic scroll isomorphic to a Hertzberg surface F1, or a cubic fourfold containing a Veronese surface, two Veronese surface, I would be very surprised if these were rational. So I've thought long and hard about the surfaces that arise, and it would be exceedingly surprising to me if these turn out to be rational in general. There was a question a while back about whether you can have non-trivial birational equivalences among hypersurfaces without them being birational. And so the case of the cubic fourfolds containing the Veronese surface is an example of this. So there's a paper by Quan Wan Lai. Maybe I should at least, let's see, I'm not sure I can, I can't. So when I get out of screen sharing, I'll try to share the link to the paper, but there's a paper by Kwanwon Lai that shows that there are non-trivial birational equivalences among cubic fourfolds containing Veronese surfaces that just come from looking at linear series of quadrics cutting out the surface. So it's possible for there to be birational equivalences even in situations where rationality is not known and probably doubtful. So the common denominator among all the known rational parameterizations is that they blow up a K3 surface. And so that's a motivation for what's coming next. So when you blow up a K3 surface or any smooth surface on a fourfold, the cohomology of the surface inserts itself in the middle cohomology of the fourfold. So the middle cohomology of the surface shows up in H4 of the fourfold. Obviously, if you have odd dimensional cohomology in the surface, that shows up in odd dimensional cohomology. Cubic fourfolds don't have odd dimensional cohomology, and so it's natural to focus on the weight 2 cohomologies that could conceivably arrive from blowing up a surface. And so the definition here reflects a hope or an idea that the cohomology that arises from K3 surfaces should be especially relevant for rationality questions. And so simply, if you look at the primitive cohomology of a polarized K3 surface, if you can embed that in the primitive cohomology, or I guess in the cohomology of the cubic fourfold, if you can embed it in a saturated fashion, then we'll say that that polarized K3 surface is associated with the cubic fourfold. And so this is what would happen if that surface were blown up in the course of modifying X. And so here's some of the basic properties. You can characterize very quickly when there exists an associated K3 surface in terms of the congruence properties of the discriminant. So as long as there are no factors 4, 9, or odd primes congruent to 2 mod 3, you have an associated K3 surface. And all the known rational cubic fourfolds admit associated K3 surfaces. There's a very nice formulation by Kuznetsov on using derived categories that turns out to be equivalent to this. I'll come back to this point a little bit later, but there is a more modern perspective that involves sheaves rather than Hodge theory that can be used to sort of get at the same kinds of quantities. And so the last thing I want to emphasize is that two polarized K3 surfaces may have the same primitive cohomology considered as a Hodge structure and not taking into account the embedding data of how that primitive cohomology sits inside the full cohomology lattice. So this reflects the fact that you could apply automorphisms that are not compatible with the extension data that come from the discriminant quadratic form. And so you get equivalence relation among these rank 1 K3 surfaces that can be relevant in analyzing these rationality questions. From the standpoint of derived categories, this is related to derived equivalence. So 2 K3 surfaces are derived equivalents precisely when they have isomorphic transcendental cohomology lattices. So in particular, that last observation has an interesting corollary. When you identify associated K3 surfaces, in many cases, they are not, in fact, unique. There can be more than one associated K3 surface. And when the discriminant is divisible by 3, the monodromy representation actually permutes in a non-trivial way the various possible K3 surfaces that are associated with this. Our definition does not differentiate between derived equivalent K3 surfaces, But so there's a little bit of sort of a loosey-goosey aspect to it. We're only looking at the polar, that lattice. But nevertheless, however you make that assignment, the monodromy representation acts non-trivially on the various assignments. And so there are cases where no matter how you make the assignment, you have to get at least 2 K3 surfaces involved. And so it raises an interesting question. Can you have a diagram like this where I take P4 and I blow up 1 K3 surface and I get a cubic fourfold? I take P4, I blow up another K3 surface that's not the same as the first K3 surface. I get the same cubic fourfold. So this would give you some very interesting non-trivial Cremona transformations between P4 and itself, so that the center of the Cremona transform and the center of its inverse are have the same transcendental cohomology. Yeah.
Brendan, I'm sorry, definitely you can't get a cubic fourfold by blowing up P4. You need to blow down something, right?
Yeah, I'm sorry. So, so I would have to blow something down. So I guess here, let me say that X might be a suitable blow up of the cubic fourfold rather than the cubic fourfold itself. So, yeah, so I really just want to say that there is a sort of a birational, that there are 2 different, I should have said it more precisely, that there are 2 different representations of X as a blow up of P4, maybe blowing down other things that give rise to K3 surfaces that are distinct from one another. And so there are examples of such diagrams that we have found for other Fano fourfolds. And recently there's some work of Russo and Stagliano that indicates that that this is the case for cubic fourfolds of discriminant 42. There's a nice framework that Schunder has been exploring that would look at this aspect of Cremona transformations more systematically. And so I'll refer you to look at his work if you want to see it developed from a foundational perspective. But it's interesting that the K3 surface, you might have more than one that you have to take into account. So here is a more precise and a stronger conjecture on rationality, which is due to Kuznetsov. And so in my language, this is the assertion that the locus of rational cubic fourfolds was characterized as the cubic fourfolds that admit associated K3 surface. And if you remember, the ones that admit associated K3 surfaces are characterized by the congruence properties of D. Let me see if I can hear it. So we have this notion of admissibility that determines by what numbers are divisible into D. And so the assertion is that the rational locus is just a countable union of divisors and moduli. And these are indexed by the discriminants that are admissible. And so this was originally expressed in quite different language, in language of derived categories, that a certain part of the derived category of the cubic fourfold could be related to the derived category of a K3 surface. And over the last 10 years or so, it's become clear that these different perspectives are in fact equivalent. Addington and Thomas showed that at least over dense open subsets of the appropriate CDs, the existence of a associated K3 surface is equivalent to the Kuznetsov's original description via derived categories. The theorem of Kontsevich and Schinkel shows that rationality is compatible with specialization. And the derived category condition that this was originally expressed in is also stable under smooth specialization. So I think that this is really just a reformulation of the original conjecture that the that the rational cubic fourfolds are given by those that admit associated K3 surfaces. There are other weaker identifications between K3 surfaces and cubic fourfolds. So here you could have a situation where the where you have lattices that are embedded in a saturated way in the cohomology of the cubic fourfold, but the embedding of the cohomology into the K3 surface is not saturated, but has a cyclic co-kernel. And so if these are called twisted K3 surfaces, is characterized as having a certain Brouwer class, which represents the twisting data. So there's a relatively straightforward characterization of which discriminants admit these twisted associated K3 surfaces. So in terms of the fact that that if you have primes congruent to 2 mod 3, they have to appear with the appropriate exponents. And so in the case where I is actually an isomorphism, this is the notion of associated K3 surfaces. But these cyclic subgroups give you a little bit more flexibility in terms of how you relate the cubic fourfold to the K3s. And so there are examples that we'll discuss where this notion is a natural one to be considering. Okay, so now let's return to the examples and the inventory of rational cubic hypersurfaces from the perspective of this classification theory. So, so here I tabulated the discriminants to give you an indication. So let me actually go back for a moment. So as mathematicians, we don't use a scientific method officially, but in practice, I think we often are convinced by having results that support a hypothesis. And so for a long time, I was a little skeptical of this conjecture because I did not know of new examples that would be found covering Ds other than 14 that would support this conjecture. And I expressed the skepticism before, and so now I'm here to sort of eat my hat. And so that skepticism appears to have been not justified, because in the last 3 or 4 years, there's been numerous beautiful examples of new classical constructions that provide, I think, quite compelling evidence that this conjecture is a right way to think about this. And so I want to present that evidence now. So here is kind of an inventory of discriminants. So here I'm looking at the discriminants that can appear for special cubic hypersurfaces of various types. So D is congruent to 0, 2 mod 6. And I indicate whether there's an associated K3 or whether there's an associated twisted K3. And so the plus means you have it and the minus means you don't. Hopefully I tabulated it correctly. And so the purpose of the slide is just to give you an overall sense of where things stand from the perspective of this classification. For the bolded discriminants, which are 14, 26, 38, and 42, rationality is now known. For the red discriminants, and so these red discriminants are cases where you do not have associated K3, but you have a twisted K3. Rationality holds for accountably many codimension 2 loci in the moduli, or divisors in the relevant C of D. These divisors, in fact, are characterized in that the twisting structure, which is a Brouwer class, is annihilated by some algebraic cycle on the cubic fourfold. And so those algebraic cycles, they appear in codimension 2 loci and moduli. And so in the red cases, in discriminants 8 and 18, there are a countable number of codimension 2 loci that sweep out or have as closure the corresponding C8 or C18 that parameterize rational examples. So let me say a little bit more about the specific results. So one of these results goes back a long way. So if you look at X and C8, these are the cubic fourfolds containing a plane. The twisted K3 surface has long been well understood. So what you have a quadric bundle that arises from projecting from the plane. And that quadric bundle gives rise to a degree 2 K3 surface by looking at the maximal isotropic subspaces of the quadrics. In a Brouwer class, that corresponds to keeping track of the sort of the conic bundle over that double cover. And if that conic bundle has a section, that's equivalent to the quadric surface fibration having a section, and that's equivalent to the Brouwer class vanishing. And so this is just, so you basically encode the section of that fibration over P2 into when a appropriate Brouwer class on the auxiliary K3 surface vanishes. And so this is in some sense the prehistory of the subject. This example will add today to at least my understanding of the twisted objects. They are naturally associated with various special cubic fourfolds. A more recent bit of evidence in this direction is work that was done with Addington, Chinkel, and Varley Alvarado a few years ago. And so if you look at cubic fourfolds of discriminant 18, we obtain, again, a degree 2 K3 surface, and now a 3 torsion element in the Brouwer group. And when that 3 torsion element vanishes, the cubic fourfold is in fact rational. One proves this by fibrating in sextic del Pesto surfaces and keeping track of when they have a 0 cycle of degree 1 and using that to bootstrap to get rationality. This is probably the main point of overlap with my talk yesterday. And so in both these cases, you get a countable union of codimension 2 loci and moduli where you have rationality. I just want to point out that this supports the Kuznetsov conjecture because the rational parameterizations that you get in these cases, they do in fact involve K3 surfaces. And so these loci in C8 and C18, they're contained in the intersection of the admissible special divisors. So in some sense, killing the Brouwer class here, the alpha, it has the effect of turning the twisted K3 surface into an honest K3 surface. And so that's reflected in the cohomology by having an associated K3. So these cases of degree 8 and 18, they support the philosophy and they show that when the twisting data disappears, then you have rationality. It is possible for these twisting data not to disappear, but you can have rationality for other reasons. So the twisting data is not determinative, but it is enough to force rationality. And so these are examples in codimension 2. So now let me ask a couple questions about these things. So here we've looked at examples where the Brouwer elements were 2 torsion and 3 torsion. How about 5 torsion? So the case of discriminant 50, if you go back in my chart. So 50 is does have a twisted K3. It does not have an associated K3. And so can we get some kind of rationality result? It's a little strange that there's a 5 torsion element. I'm not sure how to use a 5 torsion element to control whether a surface has is rational. I wonder whether it would be easier to look at stable rationality here. I'm not sure, but I think that this is a case that probably deserves some additional thought and study. I think 50 is right at the limit of cubic fourfolds where we have a reasonable chance of characterizing the surfaces. So there is nice work of Howie Newer that actually looks explicitly at what surfaces arise. And this is just at the boundary of what his techniques shed light on. An easier case would probably be the case of discriminant 24, where there is a twisted K3 surface underlying a sextic K3. And so this is, you can see here, there's an order 2 element of the Brauer group. And so here the geometry is probably somewhat more accessible, but I'm not aware of any cases or any results where you show that the vanishing of this Brauer class on the degree 6 K3 surface forces rationality. I think that this would be an interesting test case of the philosophy.
Brendan, and do you have a construction of this degree 6 K3 from the cubic fourfold in this case?
Yes, but I don't think I want to try to summarize. This is the kind of thing where I don't think I want to summarize it. Let me just say roughly that in the Fano variety of lines to the cubic fourfold, which is a hyperkähler fourfold, there is a distinguished ruled subvariety. This ruled subvariety is an étal P1 bundle over a degree 6 K3 surface. But the étal P1 bundle really is étal. It is not associated with a vector bundle on the sextic. And so the corresponding ruled surfaces associated with the fibers, they are sextic ruled surfaces with a single double point, if I remember correctly. And so, I think that's it's about as much as I can say without a blackboard. I'm sorry.
Thanks.
Yep. Are there any other questions?
Maybe you also have a construction of a K3 in degree 50 case?
So I think, let's see. For degree 50, I am less clear. I mean, there's probably something I could do. Well, here's what I expect should be true, but I haven't checked it. So there's a work of a Bayer, a long list of authors I'm not going to repeat, where they systematically produce higher dimensional hyperkähler manifolds that encode the cohomology of cubic fourfolds. And I imagine that for one of these high dimensional hyperkähler manifolds, there is a distinguished subvariety that corresponds to an étal, maybe an étal P4 bundle over the degree 2 K3 surface. And so the Bayer-McCree description of extremal rays and hyperkähler manifolds, in principle, it would allow you to say, oh, one of these high dimensional hyperkähler manifolds, there is such a subvariety, an étal P4 bundle over a degree 2 K3 surface. But I have not done that check. So I think it would be worthwhile to actually see if you can produce this ruled subvariety in the auxiliary hyperkähler manifold. The dimensions would have to be fairly large. So it's not something that you would see just by looking at the variety of lines. It would be considerably larger dimensional.
Thanks.
So the other thing I want to mention is, so Russo and Stagliano and a remarkable group of papers released over the last 3 years have completely changed my expectations about the rationality questions. And so I can't do this talk without mentioning these examples. So if you have a cubic fourfold of discriminant 26 or 38 or 42, they in each of these cases, the underlying cubic fourfold is rational. And they use pretty intricate geometry of to get these. So in the first case, they look at a special septic scroll, which is relatively easy to understand from the standpoint of the varieties of lines. The variety of lines here coincides with the Hilbert scheme of length through subschemes on the K3. And so you expect these septic scrolls. And they study the projective geometry of these septic scrolls with 3 transverse double points and show that they can obtain a rationality construction. There are similar constructions that that are valid for a C38. There's another set of scrolls, rule surfaces with 6 double points. And then for C42, the construction is a bit more intricate. It still involves a rational surface, but it's not ruled. And so the relationship between this and the hyperkähler structure on the variety of lines is less clear to me. So I think it would be very interesting to try to understand this classical projective geometry and relate it to the more general approaches for producing hyperkähler manifolds connected with X. And so these are the first new divisorial examples that have been scientific, these are the products of the scientific method. These are, experiments that support the hypothesis that the existence of associated K3 surface is sufficient to guarantee rationality. And so let me just go back to the tabulation. So the first 4 cases where there are associated K3 surfaces, we now know that the corresponding loci and moduli parameterize rational varieties. So the constructions that Russo and Stagliano do involve looking at, well, if you remember the construction that I gave for the quartic surface, we looked at the secant lines to the quartic surface, and we showed that those secant lines were indexed by a rational variety, and we used that correspondence to prove rationality through a residuation construction. And so this is the underlying insight in the other cases, but the residuation constructions are much more complex. So they look at conic curves that are 5 secant to the prescribed surface that I indicated in the previous slide. The parameter space for these happens to be rational, and using the residual intersection, you take the conic, you intersect it with the cubic fourfold. You have 6 points. You throw out the 5 points you start off with. You get a birational map between this rational parameter space and X. The degree discriminant 42 construction is even more involved. So it uses twisted cubics that are 8 secant to the prescribed surface. Here it's interesting that because of the monodromy representation that I described, so there are in fact 2 families of these special degree 9 surfaces in the cubic fourfold that are interchanged in the monodromy representation. And so we get 2 distinct but derived equivalent K3 surfaces arising as the centers. The Russo-Stagliano approach to this is heavily reliant on Macaulay 2 computations. And so I have been looking closely at the Macaulay 2 computations, but I don't have a human readable description of why there are degree 42 K3 surfaces arising from their construction. I think that this is something that we would really like to have, to be able to give explicit linear series inducing these parameterizations, like the explicit linear series that are valid for the discriminant 14 case that I described at the beginning. So, I think that this would really help to shed light on what's going on and how many parameters the construction depends on. So let's see, I think I have gone on for quite 59 minutes. All right, then I should definitely stop. I don't want to abuse your patience. Thank you very much.
Okay, thank you very much, Brendan, for the very nice, complete and clear talk. So does anybody have any questions, further questions?
May I ask a question, Professor?
Yes, please.
Yes. A result I know is that the torsion part of the Brouwer groups is isomorphic to the torsion part of the indecomposable higher Charles cycles. So I'm very interested in the Ajak cycles on the associated K3 surface. So my question is that is there any known result about the relation between the original cubic fourfolds and the Chow cycles, Chow groups or the Ajak cycles of the original cubic fourfolds and that on the associated K3 surface or maybe the pan varieties?
Yeah, I'm embarrassed to say I don't know. I don't know cases where the higher child groups have been used to address these specific problems for complex varieties. I think that there are things that were done in looking at surfaces over non-closed fields where higher child groups do come into play. But I don't know examples of there being applied to defining a complex birational invariant of fourfolds. There may be someone in the audience that knows more about this, but I don't know an example. And I think it's very reasonable to try to use a full panoply of sort of motivic machinery to try to extract invariants. I don't know an example where that's been done
I see.
in this context.
Okay, thank you.
So any other questions? Anybody?
I have a question. So in the work of Rousseau-Stagliano, how is it proved that the generic cubic of this discriminant contains a ruled surface or a rational surface? Is it easy to see?
I don't think it's easy to see. So I think that they basically do a lot of Macaulay 2 computations. So I think that the cases of the ruled surfaces that I described, there are ways of proving it. So you know that you expect it based on the Hodge theory. And so the only question is whether the self-intersections are transverse. Obviously, you could have ruled surfaces, Claire, you showed me this a long time ago. You could have ruled surfaces that are associated with rational curves and a variety of lines that have more complex singularities. And so the key thing is to show that there exists a surface with the transverse singularities of the expected invariance and that it's contained in a smooth cubic hypersurface. And so that kind of computation can be done using a Macaulay analysis. You prove one example where you have the transversality, and then you conclude that the transversality holds across the board. So this is a way of showing that there exist ruled surfaces with transverse intersections that sort of explain these special classes. I think that most of the arguments in Rousseau and Stagliano take this form, but I'm still doing my best to understand all of the specific surfaces that they consider. The ruled surfaces example, for instance, for discriminant 42, is independently verified in a paper by one of my students, Kwanwon Lai. So he gives a careful computation that there is an example in, I think, in the appropriate degree that has transverse singularities.
Okay, thank you.
Maybe could I ask a question?
Please.
Are these types of techniques expected to say something in the case where you maybe take P4 and blow up a surface that's more general, like general type or something like that, like maybe a low degree general type of surface or something like that?
Yeah, so I think that I think it's harder to recognize. So K3 surfaces are really special because we kind of know them when we see them. It's harder to recognize if I just give you a general weight 2 Hodge structure, if it doesn't look like a K3 surface, it's not quite so clear where to look for a surface that would represent that Hodge structure. And so I think there's been relatively few cases where people have explored these in situations where the hypersurface looks to be of general type. The one exception, I guess, is so I mentioned this example at the beginning, the 2-2 hypersurface and P2 cross P3. So in this case, you get a surface that is, sorry, takes me a second to scroll. So in this case, for these hypersurfaces of bi degree 2-2, the Hodge numbers are 3, something large 3. And so the surfaces that you get are general type. In this specific case, they are double covers of P2 branched along an octic. I think if you were to look more generally at hypersurfaces of bi degree ND, N2, so things that are still, let's see, the other way around, 2N, so things that are still, N2, things that are still quadric surface bundles over P2. The surfaces that would arise as centers would be double covers of P2 branched along successively higher degree plane curves. So this is one situation where you do see surfaces of general type. Carlos, does that answer your question?
I guess so. Yeah. I mean, maybe but this might be a question for Sasha also. But is there a conjecture that would say something similar in those cases, for example? And do we have? I mean, do these couple of examples say anything about that statement of the conjecture?
I think that the derived category philosophy. So in every case where you have a quadric surface fibration over P2, you have the sort of the double cover that comes from the rulings, and then you have a Brouwer class, or I mean, in some sense, you have a twisted surface of general type because you have a surface of general type along with a Brouwer class. And if the Brouwer class vanishes, then you expect to have rationality. And so I think that Sasha and maybe co-authors have explored this pretty systematically. So yeah, so there are example quadric surface vibrations are pretty well understood from this perspective. Of course, there could be rationality constructions that are sort of orthogonal to this. You know, things can be rational for other reasons that you wouldn't pick up necessarily from this twisted surface perspective.
Okay, thanks. So let's see. So maybe any further questions from the participants? Okay, if not, let's please thank Brendan for the nice talk. So thank you, Brendan.
Thank you for the invitation.